Okay, our next presenter is Professor Karl Johansson. His name is Karl Johansson, who is going to talk about how to automate road freight transport and its consequences for traffic conditions. So Karl is a professor at the School of EECS, and he's the Director of Digital Futures at KTH Royal Institute of Technology in Sweden. He works in network control systems and cyber physical systems with applications in transportation, energy, and automation networks. He's a member of the Swedish Research Council, Scientific Council for Natural Sciences and Engineering Sciences. And he serves on the IEEE and the IFAC, and he's currently the Vice President of the European Control Association. He's won a lot of Best Paper Awards from IEEE, IFAC, and ACM. And he's also a distinguished professor with the Swedish Research Council and a Wallenberg Scholar with the Knut and Alice Wallenberg Foundation. He's received the Future Research Leader Award from the Swedish Foundation for Strategic Research and the triennial Young Author Prize from IFAC. It's a pleasure to welcome Karl.
Thank you, Claire. Thank you for that kind introduction. And thank you so much, the organizers of this workshop, for having me, having a Swede among the Americans here. It's great to see so many of my good friends in the audience. It's good to come together. Good. Okay. And thanks also to Alex. Great talk. It's always difficult to come after you. This actually will have a little bit of relation to what Alex also talked about. How can we regulate traffic using connected and automated vehicle? But the starting point for my presentation here is a particular technology and a particular type of vehicles, namely trucks. So as I think everyone in this audience knows, is for quite some time, truck platooning has been developed. It's basically all truck manufacturers around the world are working on this technology and have been demonstrating this. And we have also been interested in that for quite a number of years, but not only the issues about how to get the trucks close together and run on a high speed and so on and save fuel and so, but we've also been interested in going further to think a little bit about where do we come from here. So now we have that technology. So how should that now be integrated into the traffic infrastructure? So basically, how can we use that? And that would be the relation to the previous talk here. So can we use these connected trucks actually in order to control traffic? And how should that be done? But it also, I would also like to talk a little bit about the broader perspective, because trucks are there to transport the goods that we are consuming. And that transportation logistics, how does that system change now with this type of technology, and what scientific challenges do we have? But let's talk a little bit, come back to the basic problem here of traffic control. So what we have today is mainly this type of Eulerian control, where we have stationary observers of flow and where the traffic is being controlled from a fixed infrastructure, like this type of digital road sign or ramp metering and so on. And what we envision now, and where quite a few groups are working on now, is to think instead about a Lagrangian approach. So where instead the traffic control is now based on mobile sensors and actuators. So in these situations, we would then envision that we have access to certain type of vehicle information, and this information gives us now possibility to estimate or learn about the traffic state, and we can use that now to actuate. And what is particular here is that I'm not interested in connecting every vehicle or any type of vehicle. Namely, I'm interested in the trucks, because It's a very particular type of vehicle that come from a number of manufacturers, and they are driven today by professional drivers. So it's a type of technology deployment which might actually happen, as argued by many, faster than some of the other automated techniques that we see. And another very nice features of trucks, if you haven't been traveling in one, we are going in one now down on the right-hand picture there. You see a truck is typically going slower than the rest of the car traffic. In Sweden, we go about 10, 15, or sometimes 20 kilometers per hour slower than the cars. What is a consequence of that if we have such a platoon? It means that that platoon is basically, as you see to the left of in this picture, we are basically blocking some of the lanes. So in this case, with this gray truck here, we are blocking one lane, and the cars are only going in 2 lanes. So we see that that truck is acting as a moving bottleneck. And we get now this interesting phenomena that we are basically reducing the capacity by moving this truck, not letting it be stationary, of course, but moving it slower in the traffic flow than the rest of the cars. So based on that now, we can form control problems or a control architecture that looks like you see on this picture. So here I have color-coded the density of traffic. So light color here, yellow, means that we have a traffic jam, and darker color means that it's lighter traffic density. So now if we have information about the traffic density ahead of us, we have a truck or a truck platoon here to the left. We could then utilize that information and assign a velocity trajectory for the truck platoon in such a way so that the rest of the road traffic is influenced by that and is now moving perhaps a bit slower towards this traffic jam. So let's look at that in this density diagram. I swapped the axis here compared to what you saw Alex show. Now we have road distance on the x-axis and time on the y-axis, color-coded. Lighter color means a heavier density. So a dashed black line in this means we have a car that goes in constant velocity. The light color code, the yellow area here, is a traffic jam, which is building up about after 40 kilometers, and then it's moving backwards in space, forward in time, as you see here. If we now follow a truck platoon in this diagram, what you see is that the truck platoon, first of all, you see it's moving a little bit slower than the cars, just as I indicated earlier. But then when we come to this congested area, it's moving even slower, right? And then we come over on the other side. So now with this type of controls architecture I showed here, we can now control then the platoon in this way. So we let the truck platoon go even a little bit slower, as you see here, and then we regulate it in such a way so that we hit the traffic jam exactly at the point when it's being dissolved. So if we do that, and if we compare now the right-hand plot with the left-hand, you see that what has happened is that we have slowed down a few of the other vehicles that were behind. So we basically blocked them partially by this moving bottleneck. So the question now that we would like to ask ourselves is, of course, we slow down this traffic, but by slowing this down, did that do something good or only something bad for that traffic? So basically, how did we affect the traveling time for the rest of the cars? So again, to the left here, we have without our control deployed. We have a congested area here to the right. And in this particular case, we have a total travel time increased of 38%. With now the controller in place in this case, we are shifting, as you see, congestion. We are basically smoothing out the congestion over a bigger area. And the consequence of that type of control strategy is now that we have an increased travel time compared to no congestion at all, an increase which is only 8%, which is of course much smaller than this 38%. In this particular case, we assume that we have perfect information, but in practice we would not have perfect information, right? So another thing that we are looking into is how we can actually estimate a traffic state reconstruction based on this type of dynamic assigned vehicles, if you want these trucks that are traveling or other type of vehicles, and how now they can be used also for doing control in this setting. So let me just illustrate a little bit the idea that you see here. So in this case, we have now probe vehicles. I indicate them by red. They are traveling here. If this is the first probe vehicle, you see that in the traffic state reconstruction here diagram to the right, I don't know that this is a congested area because there was no probe vehicle going between these two vehicles. So this yellow area I didn't know, but when this second probe vehicle come in, I would be able to detect that there might be something going on in this area. So by that, then I could, so to say, switch on more of my sensors, more of my probe vehicles, and build up a better estimate about the traffic state here. If I then come to the conclusion that there is actually jam going on, I could then also start acting with this vehicle, with these trucks that are moving through the flow that I have. And I can continue doing that. And then when there is no jam any longer, I can switch this off. So let me now, with the last couple of minutes here, just, so to say, zoom out a little bit from this picture. In a sense, what I try to argue here is that we could start using these trucks to control traffic. If you want, you can think about that as a kind of a service, right? It's some sort of mechanism that we can see that since we have a large number of these long haulage trucks deployed in US, there are a few millions. In Europe, there are 2 million traveling around. So if we see them as an asset here in our system, we can think about what type of services should we develop. So what we basically have talked about now would be a type of service to society which would improve traffic conditions, and in that sense also reduce the environmental pollution and so on. But we can also think about this from the viewpoint of cooperation. So we can, as you see down here to the left, we can think about the trucks that are traveling across Sweden in this case, and how this now could be cooperating in order to save energy or to save the amount of human interaction that is needed when these truck platoons are traveling. So there is a lot of interesting aspects in that problem that we and others are considering at the moment. I won't have time to go into it. Maybe in the discussion we can talk more about them. One aspect here, let me just mention that one interesting aspect is about the data. If we think about the type of data that we are sharing with Uber when we used to go with them or other type of traffic means, we basically allow to share our intention. When it comes to business data or transport data from these fleet owners, it might not at all be so obvious that you would be willing to share that even with some sort of a centralized entity. So one might want to develop this type of cooperation algorithms with guaranteed levels of privacy, which is something that we have been studied. There is also, when we talk about deployment here, a very interesting aspect about autonomy. So what level of autonomy should we expect, and on what level in this hierarchical system that I'm describing? So with that, when we come even down to the lower level, and if we're thinking about fully automated system, there are a few of us who think that we will have them, these self-driving cars or self-driving trucks, in the near future. But another piece of technology to support still this type of architecture to be developed is the concept of a traffic control tower. If you want, to some extent, is inspired by the air traffic control tower. So this is what you see here. For instance, to the left is what the a startup here in Sweden is being developed right now, Einride, where you have these remote operators that helps under certain particular circumstances when the truck needs to have some support. So in this case, in this truck there is no driver at all. But in other instances, there might be drivers in some of the vehicles, but not in some others. And this pose quite some interesting challenges. Basically, where should the intelligence reside? Where should the artificial intelligence in this system reside? And where should the human potential intelligence here be integrated, and when? So with that, I would like to thank you for your attention so much, and back to you, Claire. Thank you.
Thank you so much, Kalle.